Hello, I just wanted to show you something real quick. So I've been using Excel to plan some stuff that I want to build, and it's really useful, but some things are just really irritating. Like, it's not very simple to convert things. So let's say I've got this fib function here. Yeah, I should probably explain what this is. So I'm designing a screen that should speed up a lot of the things that like slow Minecraft down right now. And that's the first thing is most screens just have an XY decoder, and that's quite simple, and it lets you input anything into anywhere. But let's say if you have a really dense image, you still need to write each and every single coordinate, and usually the fastest you can do is 3 ticks. So let's say if I have 8 by 8, that's 64 cells. 64 times 3, it's like 192. Yeah, 192. That's 19 seconds. 19 seconds for an 8 by 8 screen. And it just gets worse from there, because if you want to display something larger, then yeah, it's just 3 ticks per pixel. That's the fastest you can do. So I really wanted to design something that was a lot faster. It's going to be a lot more complex, but that's a given with the speed. So this is a double issue page screen. So what that means is that you can store 2 pages at any given time, and that's basically dual write. So a lot of people might have heard of dual read memory. So that's a type of multi-point memory. So you have one write with multiple reads, and that's really useful for 2 operand systems or 3 operands. So you can do C equals A plus B. So you can read 2 items and write 1 item at any given time. And what double issue is, it's basically dual write. And the logic for that is quite simple, but the logic to actually drive it is a lot more complex. And I really needed an example to work towards, so this is why I did this. So Fibonacci is super simple. It's you take 2 inputs and you add the last input, basically. So 1, 1, those are my inputs. And then this is 1 plus 1, this is 2 plus 1, and so on. And then this over here is just a way to represent it in binary. So I've got the base function here, takes in this value, and it sets it to base 2, and the bit width is 48 bits. And that's all there is to it. And then I just copied and pasted it down here. But I really needed a way to represent what it would look like in memory. And to do that, I'm pretty much the only way it was going to be nice is to put every single value into its own cell. But actually doing that was quite hard, and I had to do a lot of like searching around to figure out what to do and tinkering, and and I'm not a programmer, and I don't use Excel much to actually like do functions and stuff, so this was quite difficult. But yeah, so this is the finished product. So if I go down to 51, and this is all of this represented in memory, kind of. So this is what it would look like if your memory was just mapped out like this. So here I can easily select a page. So my page size is going to be 8 by 8 bits, which is 8 bytes. 1, 2, 4, 1, 2, 4. So yeah, so this would be one set, or this would be one page for the screen. So you'd send all of this data to the screen, and then you'd send this page, and this page, and then this page. So that would speed up. I don't know how much it'd speed up, but this would be this is 48 wide and 22 high. No, 44 bits high and 64 elements. So pretty much, yeah, you're splitting the task up into a more manageable chunk, because now you can send like 3 pages high and 4 pages long. So the speed up will be a lot more than having to go through all of this row by row. And the thing about the normal XY decoder screens is really useful for just drawing lines. So if you just wanted to do Breezenham's line drawer, you only need to input 1 pixel every so often, right? So it's fine if you can only update at 3 ticks per pixel, because the Breezenham algorithm will take multiple cycles. So by the time things are ready, it's already been processed by the screen, so that's fine. But if you need really dense information like this is basically it's just a bitmap of Fibonacci, 64 elements. Like just representing this, you have to draw like more than 10 pixels just for this tiny bit of the screen. So if you have high pixel density, it's really inefficient to just do it one by one. Yeah, so I'll tell you a little bit of why doing a paged issue, multiple issue screen is you can see how the speed up happens, but the reality of that is you need a nice way to actually represent the addresses of the pixels. So my initial idea was to have it 8 bits. You set the bandwidth of the screen would be 8 bits, and you send up to 15 different pixel addresses, along with a global operation if you want to. That's just MISC pretty much right now. And then the pixel page length. So the pixel page length will tell you how many pixels are in the header. But I've realized that's not very efficient because I have a 16-bit CPU architecture anyway, so I may as well just send this all at once. So that's what it's like here. So the page length would be in page 0. So I need a way to actually read that length, decide whether this page is the only page holding the coordinates for the pages, or look at both pages. Because if this was 7, if this held 7 addresses, I'd want to fill this with a pixel, right? Yeah, I don't want to waste space. So I'd need a nice way to take the pixel length, calculate how long I'd have to wait, and then the only other way I've figured out how to like orchestrate, coordinate between the CPU and the screen would be to send a reply. And I need a way to calculate how soon I can send a reply, because I don't want to have to wait until all of it's done, then send a reply, because that increases the latency. So I can assume that after X cycles, this is going to be done, so I need a way to do that. So it's quite a complex challenge that I have to figure out. But yeah, that should work. So yeah, so they said send a header file, a header page, well, 2 header pages but in parallel, and then that would coordinate each following page to be addressed to its proper thing. So I need a way to figure out if I need to look at both pages for coordinates. I need to have a way to store these coordinates for when each page comes, and then I need a way to talk back and forth between the page and the whatever CPU. and this will help me figure out how to actually like address each pixel in like when you generate in a program, because the fib program is like 3 lines, but then having no XY coordinates on the actual like for each pixel changes the kind of challenge, because initially you'd have to convert this number into a set of coordinates. So this number would take 1, 2, 3, 4. Like just this part would take 4 different coordinates. You'd have 4 different coordinates, but now I don't have to generate coordinates, but I need to generate like a grouped coordinate for just this page. So this is going to be helpful for that. But yeah, that's all I wanted to show, really. Yeah. I'll put this in the description because it was really annoying for me to figure out. So I'll put that in the description. I don't think you really need to see all of this stuff. Like, that's pretty simple. You just adding, and then the base function. But yeah, dips. That's what I'm planning. But yeah, I hope you enjoyed this random video. I don't plan on being active. I just wanted to just update, not really even update, just show you this cool thing that I made in Excel. I think it's cool anyway. But yeah, catch you later.